This is the video introduction to Activity 3.1, Graphing with Real Numbers and Absolute Value Functions. In this activity, we'll learn to extend the idea of working with discrete data points, individual tile figures, to working symbolically and graphically with real number function inputs and outputs. We'll find the domain and range of some basic functions and describe them using number lines, inequality, and interval notation. We'll also learn about absolute value tile sequences and their corresponding symbolic and graphic forms. We'll use black and red tiles. The domain of a function is the set of allowable inputs. We use the domain of counting numbers, n is 1, 2, 3, etc., to describe the input, so just figure numbers, for activities 2.1 through 2.4. And in activity 2.5, we extended our domain to the set of integers. Remember, we had negative figure numbers. In this activity, we'll extend our domain options to include real numbers. The range of a function is the set of possible outputs for a function. We've seen many possible ranges. For example, if our function is f of n equals 2n plus 1 with a domain of counting numbers, the range would be the numbers 3, 5, 7, etc. If the function is g of n equals negative 2n, again with a domain of counting numbers, those figure numbers, the range would be the set of numbers negative 2, negative 4, negative 6. Those are the only numbers you can get. The set of real numbers is the set of all the numbers on the number line, and it's the union of the rational numbers and irrational numbers. Rational numbers are the numbers that can be written as the ratio of two integers with a non-zero denominator, so 2/3 or 17/4. Irrational numbers, such as the square root of 2 and pi, are numbers that cannot be written as the ratio of two integers. We will now graph and model all of the points. In Chapter 2, we plotted distinct coordinate points corresponding to tile sequences and functions defined with the figure number inputs and net value outputs. In many cases, it felt natural to connect those dots, even though there really weren't figures for input numbers such as 0.5 or negative 2.1. You may have also noticed that even though there weren't those figures, symbolically it did make sense to use numbers other than the counting numbers or integers as function inputs, as our function domain. We will now extend our working domain and range to include the real numbers and subsets of the real numbers so that we can, in fact, connect the dots and graph all of the points. In some cases, we may be able to sketch actual figures corresponding to rational number inputs, such as a half or a third. Of course, we can't actually do that with algebra pieces, but we can always do sketches of partial figures, partial tiles. Overall, we'll use extended tile figure sequences to find the pattern, and then we'll use symbolic function rules to determine additional coordinate points on the function graphs. We can then precisely connect the dots and complete our graphs. We'll now use x as our independent variable and y as our dependent variable. We'll use x instead of n, that's our input variable, and y instead of t, that's our output variable. So, for example, we might write y equals f of x instead of t equals f of n. This just helps us keep track that we're working now with real numbers. And similarly, when we use our white and opposite white strips, we'll now label them with x's and minus x's. We need to be able to show and describe real numbers and subsets of real numbers, and we'll do this in three ways: with number lines, inequality notation, and interval notation. In the following examples, remember you could use lots of different variables with this notation. It doesn't have to be just this example notation. Our first example is all real numbers. On the number line, the entire number line is shaded. The entire number line is shaded here. For inequality notation, it's negative infinity is less than x is less than infinity. And for interval notation, we use open round parentheses from negative infinity to infinity, and you can read this more elaborately as shown here. For example 2, we look at all real numbers greater than 0. Here, the 0 has an open circle, and the number line above 0 is shaded. Our inequality notation has two options. We could write x is greater than 0, or 0 is less than x is less than infinity, and read that as all x greater than 0. Our interval notation is an open parentheses 0 to infinity. For example 3, all real numbers greater than or equal to -1 and less than 3, we are including -1. So on the number line, -1 is a solid circle. We are not including 3. That's an open circle around 3, and then the number line is shaded between them. The inequality notation is -1 is less than or equal to x is less than 3, and the interval notation is a square closed bracket, -1 to +3 with an open bracket. The fourth example is all real numbers less than -2 or greater than or equal to 0. The number line below -2 and 0 and greater are shaded. Below -2, there's an open circle and then shading down, and then including 0, the solid circle, and up. The inequality notation is -infinity is less than x is less than -2, or x is greater than or equal to 0. Those both have to be included. You can leave this -infinity off if you like. And the interval notation is -infinity to -2 union 0 with the square bracket to infinity. Let's look at how the number line works. For less than and greater than notation, use an open circle around the number to indicate that the number is not included. For less than or equal to or greater than or equal to notation, use a shaded solid circle around the number to indicate the number's included. For inequality notation, for parts all the way up or all the way down the number line, you can include the infinity or -infinity symbol or not. And all the symbols less than or equal to, greater than or equal to, and greater than that we used in single inequality must face the same direction. So that's, for example, -1 is less than x is less than 2. That's correct. Similarly, you could write -1 is less than x or x is greater than 2. That's a correct way to do that. But if you try to write -1 is less than x is greater than 2, you can see that's crossed out. It's incorrect because it doesn't make sense, because -1 is not less than, it's not greater than 2. Well, it's confusing, right? Because you have a less than and you have a greater than symbol. So the symbols have to go in the same direction. The interval notation, open parentheses are used with infinity, as you can never actually get to plus or minus or infinity. And the symbols less than and greater than correspond to open parentheses, those round parentheses, and the symbols less than or equal to and greater than or equal to correspond to closed parentheses, those square brackets. And for two disconnected intervals, so as we saw in example 4, we use a union symbol. And finally, in this activity, we'll do a lot with absolute value. And so a reminder that the absolute value of a number x is denoted with vertical lines around the x. And the absolute value of x is simply x if x is greater than or equal to 0. And the absolute value of x is -x if x is less than 0. So for example, if I put in -2, -2 would be positive. The answer is always positive or 0. And note that although 0 is neither positive nor negative, we define the absolute value of 0 to be 0.